Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, it's a pleasure to welcome Ed Dawson today. Ed has probably been with the ISCR longer than I have, even, which is good and sad in some ways, I guess. I don't know. We've been too long. Ed is actually a local. He went to high school around Olympia, is it? But has been at the Queensland University of Technology for more than 35 years, I think.
Yes.
So he's been in all aspects of crypto for many years, in many ways. And today he's going to be telling us about efficient elliptic curve point addition. But first, I think just a brief overview of the Information Security Institute at QUT.
Yes. Okay, I'd like to thank Josh for inviting me here. As Josh mentioned, I originally came from Washington State. And Josh, I guess I come here either before or after crypto over the last 20-some years. I usually end up in Washington State to visit family and that. And I've been speaking to Josh for quite a number of times to come here. And it's my pleasure to actually finally to be here now to visit Microsoft and that. I should say that I was just to age myself, I was just at my high school just by chance. There was a 45th high school reunion, which I went to for Olympia High School on Saturday night. So I born and raised there in Olympia. I went to the University of Washington, undergraduate degree. And then in the early 70s, and probably I don't know if anybody was around here, probably not at that time. At that time, there was a bit of a problem in this area. The unemployment rate was 20%. Imagine no Microsoft, okay? And the government shut down this SST and program for the supersonic transport, and the unemployment rate was 20%. And the saying was, "Would the last person that leaves Seattle please turn the lights off?" So I took the advice of a famous person from the 19th century called Horace Greeley. And he said, "Go west, young man." So I went west, and there was no further to go west here, except you had to go across the ocean. So I ended up in Australia in 1971, and I've been there in Australia since and that. Okay, so first of all, I'm just going to give you a brief overview of let me just grab this thing here, of our institute. And I'll pass these around, I got a couple of these, and I'll leave these here, just describing some brochures describing our institute at QUT. I was the research director of this for like 15 or 16 years, but 3 years ago I took a golden handshake, so I just work 3 days a week now, and I'm an emeritus professor in that. So we were formed originally in 1988, which is sort of early days at universities in forming centers in information security. And originally we were just in the area of information technology, and we had crypto, network security, and trusted computing. But in 2005, our university decided to look at the wider issues in information security, and we combined research from 4 different faculties to do research across, because as all of you know, that we can work in our crypto world, but there's also issues, legal issues, and all sorts of other issues related into using our information security. And so that's what we looked at in terms of business, really wants to look at a multidisciplinary approach. So that's what we adapted at QUT in 2005. And so this is sort of our aim. I won't spend much time on that. And this is what the size of who we are. We have a large number. Most of those students are PhD students. About 90% of them are PhD students. So in size, we're equivalent in size to any other group that I know in the world at a university. In the United States, a similar university to us would be Purdue University, would be similar to what our group at QUT is in that. And just to finish this section then, that we work across, my main interest is in crypto, but I've also worked in e-business and e-government with applications. We have a legal section, network security is still with us. And then we also bring in, we have a large number in the engineering side who are working in biometrics and surveillance area. We have like 20 PhD students in that area. And we have risk and crisis management from our business and IT people. So that's who we are at QUT, and those brochures that I passed around, and I'll leave those here, describe us in a little bit more detail. I want to go to the next one for... Okay, so when Josh is getting this ready, the talk that I'm giving here is many of the PhD theses of my student Hussein, who's back in Turkey, and he's about ready to go into the Turkish army. Unfortunately, he's got to spend his year in the Turkish army.
Ed has kindly left me a copy of the thesis.
I left his thesis there for anybody who wants to see it. He's interested in his thesis after my talk and that. So the talk that I'm going to give today is an invited talk that I presented at the Shannon Institute conference workshop in Ireland that I presented in May in Ireland, right before Eurocrypt. So we'll have an overview. We'll look at some of our tools that we developed. We'll look at some of our inversion-free point addition. And then we'll look at some experimental results and a conclusion at the end. So if we're looking at, and this work is all concerned about implementing elliptic curves in software. So there's three different areas that we'd be concerned about if we're looking for efficiency. Is trying to get our finite field arithmetic done quickly. We could look at point additions, new coordinate systems, new and faster formula, and we could also look at scalar multiplication methods. So our work here, what's that? How does that work?
Work the other way.
So Hussein's thesis is mainly concerned with that part, although we're going to bring in some previous work, not his new work, but we're going to bring in previous work at the end when we bring in our experimental results at the end. So I don't have to, it's like teaching everybody knows it's used in crypto here. So we want to have efficient methods. The aim of his thesis was to derive an addition law on an arbitrary curve and efficient adding points on this elliptic curve using the derived addition law. And we had practical speed-ups in higher level operations which depend on point additions. In particular, the contributions immediately find applications in crypto. So we're going to go over the five, and these are the five different forms which are being used quite widely in elliptic curve cryptography. And most of the work, this is the previous work, we mentioned that a little bit, but most of the work then was going through these four different forms then and trying to define a complete addition formula and then also trying to find efficient methods for doing implementations, as we'll see. So we also found a Weierstrass curve, which is birationally equivalent to each of the curves in the standard form. And also Hussein did some interesting algebraic tools using Magma and Maple packages. Everybody familiar with those two packages in that? Our Magma is actually an Australian package from John Cannon at University of Sydney in that. I know well in that. And we looked at group law and affine coordinates for each of the studied forms, simple way of exception handling. So we're going to give, in the thesis, he has a complete algorithm for doing the addition for each one of these forms in that. And then we're going to have efficient inversion-free algorithms that we'll talk about, and then optimized high-speed software. So some notions and assumptions that we'll use. We'll use M for multiplication, S for squaring, I for inversion, and D for multiplication by curve constant. And people can argue these, but this is roughly the sort of measure that we take in comparison these different operations then.
Multiplication is addition here? You mentioned multiplication. Is that the same operation as elliptic curve addition?
That's the no. That's just field. That's the field operations in that.
Okay. So, what's the difference between plain multiplication and multiplication by a curve constant? What's special? Like the things like lambda.
Like the A's and the B's here and there.
Okay. Oh.
So the short Weierstrass form then. Here's our. As usual, when we display the elliptic curves, we actually take a real curve here just for the sake of showing the curve, and that just make it look nice and that. So this covers all elliptic curves of characteristics 2 and 3. So the work is totally concerned with large prime characteristic that we're looking at. Before 2006, this was what everybody looked at because it was the most efficient form in that. We're going to see how things have changed now over the last 3 or 4 years based on our work and the work of others, particularly the work of Dan Bernstein and Tanya Lang as well in that. So the next one is the extended Jacobi curve, this curve here. That covers all elliptic curves with a point of order 2 characteristic not 2. Oh, this is what this is the speed records that we had then for what's come out of his work in that, and this is currently the best for doubling intensive operations. And this is the mapping to change for each one of these curves. Then we're going to map. We can map back and forth between this curve and the Weierstrass curve, and this is the formula for mapping from that curve to that curve then. The next one is the twisted Hessian form, which is this curve here. That covers all elliptic curves with a point of order 3. This is again our speed records, as we'll see. And this has interesting for parallel implementations. And again, here's our this is equivalent to that Weierstrass form, and here's our mapping here then. This is the one probably anybody worked with elliptic curves has probably heard about. This is the one, as you can see, was what Tanya Lang and Dan Bernstein brought out, and then we extended there to still be the most efficient. We thought one of the ones we actually had afterward, we went back and looked at this one more and tried some more tricks, and this still came out to be the most efficient, as we'll see. And that covers all elliptic curves covered by that Montgomery curve, and that's the form here. And it's best for addition-intensive operations, very interesting for parallel implementations. I'm not going to talk about parallel implementations, but there's some of that work in Hussein's thesis as well in that. And again, the curve is that Edwards curve is equivalent to this Weierstrass curve, and there's our mapping. The next is this twisted Jacobi intersection form, which is this curve here. That covers all elliptic curves with exactly 3 points of order 2. There's a new addition for homogeneous projective coordinates, new extended, and this is our speeds here that we have in this. And here's, again, that's our mapping to map from that to that. Okay, so you can see that this is the Weierstrass form. This is the number of isomorphic classes. But you can see that we don't lose that much by going to these other curves than that. You can look at particular like the twisted Edwards ones. We can see that we lose about half the size in that, a number of isomorphic classes. But still we have a large number of classes in that.
What is QQ?
That's the field in that. That's, and again, this is and we're going to talk about. We're also going to talk about having some single curve constant, and we get more speed, but we lose a little bit of classes, but we still have a large number of classes by having single curve constants. And we're going to do some of that. We're going to have, like, if we put a 1 there, we get a little bit more speed, as we're going to talk about. Okay, so now that's a brief introduction to the curves, and I actually gave you all the results there, summarize the results, but now we're going to go into more detail. So the part now we're going to look at is we're going to develop the form for to get a complete algorithm for adding each one of these forms. Now I'm not going to go through. I'm only going to go through the twisted Edwards curve. Actually, I'm going to go through in detail for the twisted Edwards curve for each thing that we're going to do, because the rest of it, the other ones are actually doing similar sort of things, and it's all in his thesis. So I'll only go through the process to use the twisted Edwards ones, and because they're actually the most efficient ones anyway. So we wanted to automate the group law derivation to find the minimal degree point, doubling, and addition forms, and we use Magma and Maple as the tools for doing this then. And that also allows us to verify the correctness of our derived formulas, and we also found some alternative formulas as well. Okay, so this is, and I won't go through the proof of this, but this is a little theorem here which we're going to use here, is that we have two different forms. And we're going to use a Weierstrass form and some other form, and assume that there's a mapping from phi from W to M, from the Weierstrass form to the other one, and psi which maps M to W, such that those maps, the composition phi psi and psi phi, are equal to the identity maps on each of them. And let plus W be the affine part of the unique addition law on W, which we know. Then the affine part of the unique addition law on M is given by this composition. So that's the result we're going to use then. Okay, so we're going to, as I mentioned, we're going to let W be the Weierstrass form, and let this be this generic form. And we know what the group, and then we have, and plus W then is the group addition on W then. So then, if we have this psi and phi, as we defined before, mapping one to the other, such that their compositions is the identity map from that theorem, then we know what the mapping on M is then, what the addition law is. So now we're going to apply this then to the twisted Edwards curve then. So we use this curve then, and just briefly, some overview of this curve then. There's 2 points at infinity, and then we can blow them up to produce 2 other points, omega 1, omega 2, and blow up the other one. We get omega 3 and omega 4. So if we apply that rule from that theorem, this is this rule here, using the addition, plus W was the Weierstrass addition form, then the addition form in plus M is given by that. And you can see there's our mappings, phi and psi, and then we do that, and there's the addition law on W, using the standard Weierstrass addition law. And so then here's the addition law on twisted Edwards then, is given by this composition then. Yes?
Sorry, you were talking about the affine part of the addition law. Does that mean it's just your rules for adding affine points to one another? Where
Yes. We'll see how. Yes, it is. And there's some cases we'll show you how to. I'm going to give you a complete algorithm which does all of it.
Okay.
Which is going to come out shortly. Okay.
Okay.
That's at the end of this section. The answer is yes.
Okay. Thanks.
So here it is. Now, that's a mess, okay? So this is where Hussein went further in that, on some other tools. So we expected something nice, okay? But we ended up with something which is a mess, and it's not going to give us efficient arithmetic in that. So what then was Hussein and one of my other students, former students, Ken Wong, found this algorithm by Monaghan and Pierce. He hadn't applied it to elliptic curves and that. That's what we did, okay, with our work in that. This finds this is in his thesis, I think it's Pierce's thesis. That finds a fraction with a minimal total degree sum of the numerator and denominator. And the algorithm walks up through the degrees of the numerator and denominator, and in each step attempts to solve this equation mod I, where I is the elliptical curve points in that of the x1, y1, and x2, y2, and n is the original denominator, and d is the original denominator, and the other two, eta and delta, are the lower degree denominator candidates. So if you apply this using a computer algebra package to do it, you get this then. So it reduces down to that using the computer algebra package with that using Pierce's stuff. So we didn't know anybody else that had actually applied this to it, and Hussein did this for each one of these forms. Then he derived something like formulas by doing this sort of same trick for each one of those forms in that then. And then from there then, using this formula then, this is the complete then addition law, and for adding points in the twisted Edwards curve then, and that's the complete addition law with using, you can see, using the singular points and that, with all these else's and ifs and that, and you get the complete addition formula for the twisted Edwards curve then. And in Hussein's thesis, he's done the same thing for all of those forms then. Got the complete addition law. Okay, so that finishes that section then. That was the sort of computer algebra section and that he did in that. Okay, so now I guess we're going to come to the implementation part. So we're going to look at efficient group laws, develop new low-degree inversion-free formula, new and faster algorithms, and new coordinate systems and new mixed coordinates for each of the forms. And again, I'll go through this in detail. I'll give the results for each of the forms, but I'll only go through in detail with the twisted Edwards. But I'll give the results for each of them with its final results. So the twisted Edwards then, this is the work from Dan Bernstein and Tanya Lang, and this is these papers, and I'm not sure who all the other people they had with them. I got some references at the end with some of who some of their co-workers were. So then what we've done, we've got additional results. So all of this stuff, we use projective coordinates for elliptic curves then, because they're projective coordinates, then we can get rid of the inversions then. So we have additional results for inverted coordinates, a new system which is extended homogeneous coordinates we call EE, a new system which is mixed homogeneous projective coordinates EX. We have dedicated non-uniform and dedicated formulas which is faster than the unified formulas for addition. So this is the so the first two are results of Dan and Tanya. This is their with their projective coordinates and the inverted coordinates. Then, so we add another projective coordinates, and doing that we get rid of you notice there's no division anymore, so we don't have to worry about inversion anymore. And they also have an inverted coordinates. So when we look, and this is their speed records, we're going to find tricks to actually improve these a little bit. So what we observe that the high degree polynomial expressions, we can further lower the degrees by keeping the track of x, y over z separately. And by doing that, by introducing a new variable, we have x, y, t, and z then, where t is x, y over z, and then x, y, t, z satisfies that equation. And there's our formulas then for addition. I mean, by doing this, we have to actually store another variable, but in software, the storage is cheap, so this is no big deal. So by doing that, then a point addition now takes 9m plus 2d, and we can have, if a is a square in k and d is not a square in k, this actually is a complete addition then. So the brackets means that was a previous work, and this is our work. And then if you put a as -1, you can have a little bit more speed up as well. This is going through, I won't go through that, but that's going through what you can see computing this, the x, y, z, and t is the sort of thing you do in the registers and that, the sort of the formulas you need to go through in the registers and that, computing the x, y, z, and t. So then we added a little bit more trick, another little trick, just doing little tricks at the edges here. The trick here was then to have a mixed coordinate system. Yes.
So the current size of elliptic curves, each number is at least 2 registers, if not 3. So does it actually work in the registers that the architect will care about?
I'd have to ask. That's more for Hussein. I'm not sure. I'm sure you can. I'm sure he implemented all these, and so I'm going to give you the implementation in software in that.
Okay.
So he's implemented all these in software. So he wasn't. This is he's done all this, as I'll give you his speeds in that at the end. Okay, so what we've done a mixed.
256
It's 4 registers.
So for repeated doublings, he used the 2e to e system, which is this one up here. If a doubling is followed by addition, use 2e to the extended ones for the doubling step, and then followed by using in the extended form to do the addition step, and output that back in the e form then. And that's sort of using a mixed trial on that, and that gives the highest speed then, as we'll see. Now, as well, another little trick that Hussein found is that the affine point addition is dependent upon A and D given by this formula here. It has both A and D in it. However, we can get rid of the D by doing this little trick here, doing that little change in that, and we can get rid of the D. Then, if we go back to the projective forms and our extended forms, then this is the new form in those 4-coordinate system. And now a point addition is now 9 multiplications plus 1D, and that saves an extra D. And if we have a point addition with A equal to -1, we can take that down to 8 multiplications. And if you have a base point of odd order, we don't have to worry about, that big formula I gave, you don't have to worry about any exception points then if you have a base point of odd order. So then, this is our final results then for doing all those tricks together, and that these give our complete results then. Okay, so that was the twisted Edwards. For the other forms now, there actually was not that much implementation done before our work. This is the extended Jacobi, quartic. There was an addition in unified form. But these are all of our. We do the same trick as we do the same sort of tricks. Projective, extended, mixed coordinates. And you can see the sort of speeds that we have here then. And then this is for operation counts for twisted Jacobi with B equal to 1 in different coordinate systems. And again, doing the same sort of tricks. You can see that was what before our work, and these are our new results then. And the same with the Hessian form. These are the previous results, and these are our new results with all those projective, modified, extended, and mixed coordinates again. And finally, we also looked at there's a few little bit of, Hussein's added a little bit of more implementations to the Weierstrass forms as well. You can see most of that work was done previously on the Weierstrass, so we didn't spend that much time in the Weierstrass. Okay, so the last part then, we're going to look at some of the implementation here then. Some of the implementation of the curves in that. So we took the elliptic curve that, the finite field that we chose was 2 to the 256 minus 587. And then we found, and these are the 5 different elliptic curves that we use for comparison. What the H means here is that the order of the curve is that order of that curve is prime, okay? And the other one is a large prime times 2, a large prime times 3, and so forth. So these curves then, if we look in terms of discrete log attacks, then that these curves should be secure then against any sort of discrete log attacks in a polared row and so forth, because they have a large prime order for each. For each of them in that. I'm not sure what RSA is. What is that? 2,000 bits or something like that? Is that Sorry?
You typically use 2048 for RSA.
So, I mean, but that size there, what size of RSA? I'm not sure what's RSA.
That's a good, those very big RSA, like I think 16K per NSA.
Yeah, okay. Okay, so I mentioned at the start that I mentioned that level of doing the scalar multiplication, that we weren't trying to actually add anything new. We were just trying to use some of the best results there when we're actually doing the implementation. So we use this scalar multiplication from this, is it Hanscon? Alfred Menzies and Scott Vanstone's book in 03 for the scalar algorithm 3.38. In the integer recoding algorithm of the scalar multiplication, we use this algorithm from 2005. That runs on the fly as the main loop of the scalar multiplication is performed. And then we also wanted to look at if we have lookup tables, and we kept all points in extended projective coordinates. So let's look at applying to those curves then. So before 2006, everybody said Weierstrass then. So we did this on implemented this on Core 2 computer. And you can see then that the different, what this actually means in terms of speed then. That the twisted Edwards then is marginally better than the Jacobi quartic then. And the Weierstrass was the slowest of them all then, in comparison then. So we also did a comparison. We're just going to compare the Weierstrass one and the twisted Edwards in this slide. So we looked up, and then this is the size of the lookup table. And you can see then, again, having the same size of lookup tables, that again, the twisted Edwards is faster than the Weierstrass as well in that. Okay. So the goal here was to start to revisit elliptic curves and that and see if we can end up with some more efficient point additions. We applied some interesting algebraic tools to develop automated group laws. Found a way to simplify these using that Pierce's PhD thesis. Applied that elliptic curves and found that gave us a really efficient way to give us simple statements for our addition and that then. For each of those forms then, we developed a complete description of the group law. I gave you the twisted Edwards forms, but in the thesis then, there's complete addition forms for each one of those forms in that then. And that was the first time for most of those forms that that's actually been in the literature in that. I should also make the statement that a lot of this stuff is actually, he's writing a paper on this right now. We haven't published some of this work in that. The part here we published the Edwards stuff, but some of the stuff is not published yet. And then we developed high-speed software to verify the results from our inversion-free formulas as well in that. So this is some of the papers that we published then over the last 2 or 3 years. I guess the highlight paper is this one that we had in Asia Crypt 2008, where we did the twisted Edwards curve and that. Okay, thank you then.
So you use the automatic tools to derive these formulas, like the brackets you showed there. So then finally in the end you need something like, you also had like these formulas saying what the computer actually does. So
That wasn't automated. That was
yeah,
thinking.
that was my question. So that's still handwork, like finding these trees and writing down the formulas.
Actually, before he was using the computer software, he actually derived some of those by hand, some of that stuff too, and then my other former PhD student, Ken Wong, who was more of a computer algebra freak, started working with Hussein, and got Hussein working on the computer algebra. And said, "Oh no, what?" And then he said, "Oh wow, look what I can do with this stuff and that." And he went to that. But the actual derivation of the formulas, he had to actually do that by hand and that. Yeah, so it was a bit of work to actually go through all those rules and that.
And that Pierce result just gives you the minimal degree for those fractions.
Yes. Well, they hadn't applied it for the elliptic curve. We're the first ones to apply this elliptic curves. Nobody else has done this before that we know of elliptic curves and that.
Thanks.
Yes.
So I will try to derive addition formulas suitable for pairings computation.
Sorry?
Have you tried to derive additions formulas that could be used for pairings computation?
We have another. I haven't been working in the pairing work at all myself. Hussein did a little work with another one of our students, Craig Costello, and Craig's doing some more work with this and that. Now I'm not sure where he's visiting, somewhere in the United States now.
We've done some of these by hand, so like the twisted edgeworks.
But they worked. Craig and Hussein worked together for a little while, so Craig got his background from Hussein.
Well, thank you again, Ed.
Well, thanks for inviting me.